Okay, I think we can start. I think we can start because there's also a Zoom audience.
Oh, yeah.
In the room. Okay, so for today's MITP seminar and NITheCS seminar, we're very happy to have Raoul, who kindly passed through Joburg while visiting Cape Town for a conference next week, I think. He's coming all the way from Milan, and he's going to tell us about position physics at the Large Hadron.
Okay, great. Thanks a lot for the introduction. Thanks for the invitation. So as I mentioned to many of you, I was born and raised in Cape Town. So for the majority of my life, Johannesburg was a little bit north of Stellenbosch, and essentially the whole of South Africa north of Stellenbosch is Johannesburg to me. So I'm very happy to be here to be disabuse this notion. People here have been very welcoming. I've enjoyed the day and a half that I've spent here. I'm looking forward to telling you about some of the work that I do, which is precision theoretical physics for the Large Hadron Collider. And as I mentioned, I'm going to try and give a general review talk. Hopefully it'll be accessible to the non-expert, including students at the honors level, of which I understand they are 0, but also at the master's level, as well as for people who are working on completely different types of physics. And so I'm going to start off by giving a general motivation for why we would be interested in doing these incredibly difficult calculations. And then towards the end, I'm going to touch on some of my own research. But please, if you have questions, stick up your hand, interrupt me. I would much rather not finish all the material that I have, but still be able to answer your questions. I'm not stressed if I don't get to show off my own glory of the work that I'm doing at the moment. Okay, so I want to start off very generally just to discuss a bit about the role of particle physics within the broad field of physics. And so we have this idea, this philosophy called reductionism, and the idea is we can understand some of the structures of the world around us by going to smaller and smaller scales. And so we can understand things like materials or chemical reactions in terms of molecules, which are in turn made of atoms. Atoms have a nucleus at the center surrounded by a cloud of electrons. Inside the nucleus, there are protons and neutrons. And inside the protons and neutrons, there are quarks, and quarks together with electrons and other particles are the most fundamental particles that we have firm experimental evidence for at the moment. Now, reductionism has its limits. It's very interesting to understand the emergent properties of more complex systems, but you can't really deny that we've made enormous progress in the last several centuries using this idea of reductionism to understand the physical world. And particle physics is at the forefront of the reductionism approach. And of course, if we want to study smaller and smaller scales, we need a microscope or a laboratory in which to do it. And of course, there are quite a few experiments that operate in high energy physics, but the one that I am most interested in are the experiments taking place at the Large Hadron Collider at the CERN laboratory in Geneva. In these experiments, we have a 27-kilometer long tunnel. These accelerate protons to an energy of roughly 13, I think it's now 13.6 GeV, which is a very, very, very appreciable fraction of the speed of light. And then we collide these protons. This creates an enormous amount of energy, which is then converted into the production of various particles, which travel into the detector. They can be observed and their properties explored, studied, and we can use this to explore these fundamental interactions in a very controlled environment. That's the important point. Now, there are people in the audience who are particle physics experimentalists. So this is all that I know. If you want to know more about how these experiments work and how the detectors work, please go and talk to them. I'm sure they'll be happy to discuss more about it. I'm more interested in how we can make theoretical predictions that we can use to compare the experimental data against. So we're at very high energies, meaning that the form momentum squared of one of these particles is much larger than its rest mass squared. So we need to use special relativity. And since we're clearly dealing with very, very small particles, we need to take into account quantum mechanics. And these two can be joined together in a mathematical framework called quantum field theory, which is very much the language of high energy physics, or elementary particle physics, if you like. And if you add principle of gauge invariance, and you can think about gauge invariance as sort of a generalization of the gauge invariance that you know from electromagnetism. In quantum field theory, this is understood as some rotations in some abstract space. These rotations should be local, so they change from point to point. And if you impose this gauge symmetry, you can get a theory of called quantum electrodynamics, which is the quantum field theory describing electromagnetic interactions based on an abelian U1 gauge symmetry. The symmetry is the important point is that this is how we understand electromagnetic interactions at the level of electrons and photons. And in fact, we see the electromagnetic force as being mediated by the exchange of exactly these photons. So if we have a diagram here where I have the scattering, for instance, of an electron to another electron with some positron, we see this as happening through the exchange of a photon. And importantly, this photon is massless. Now, this is a very nice theory. You can use it to compute something called the anomalous magnetic moment of the electron, and you can do it, and you can get a very, very high precision. Maybe it's easier if I show it here. And then you can, people can go and measure it, and you see that the agreement is almost perfect. I think it's something like 10 significant figures. It's one of the most accurately measured quantities within all of science. You can also consider a slightly more complicated gauge rotation called an SU3 symmetry. This is a mathematically, this is a non-abelian symmetry. And if you impose this, you get a theory called quantum chromodynamics, which describes a strong force. And just like the electromagnetic force is mediated by massless photons, the strong force is mediated by massless bosons, this time called gluons. And just like electrons have a charge, the photons will couple to, the gluons also couple to a different charge called a color charge. This has nothing to do with colors that we see around us. It's just a label. In the same way that positive and negative are just labels. It's not that an electron is negative and therefore it has a slightly pessimistic outlook on life. It's just two random words that people came up with. In this case, they came up with the words of color. And you can see how long I've been outside of South Africa because I'm using the American spelling for color. Now, the important point is that gluons also carry a color charge. So we have gluonic self-interaction. So we can have a diagram where these two gluons interact with this gluon in the middle. And this, generically speaking, makes quantum chromodynamics, QCD, a lot more complicated than QED, essentially because it's a non-abelian symmetry rather than an abelian one. And this is while we know electromagnetism from our everyday lives and from our first and second year undergraduate courses, QCD, the strong force is the short range force. It's only observable at the atomic energy scale. So this is not observed classically. And this principle of gauge invariance is an incredibly powerful principle. So we've seen, I've shown you, told you that it allows us to construct quantum field theories for two of the four fundamental forces, the strong force and the electromagnetic force. There's one of the other forces is gravity, and of course, quantizing gravity is an incredibly difficult problem. It's probably the hardest problem facing theoretical physics at the moment, and to my opinion, we are nowhere close to finding a good solution to that. But we've at least managed to write down a quantum field theory for two of the four, and I'll get to the weak force in a moment. It turns out that this principle of gauge symmetry is also very deeply connected to conservation laws, such as the conservation of electric charge in QED through a very beautiful theorem due to Emmy Noether. And also it limits the pathological behavior of quantum field theories with things like anomalies and renormalization and so forth. So it's very, gauge invariance is very nice, is what I'm trying to say. So what about the weak force? You might know the weak force as the force responsible for neutron decay or beta decay, and this can be understood through the Fermi theory. But this turns out that this is just a low energy approximation to a more complete quantum field theory. However, this quantum field theory, in order to match experimental data, needs to have a massive force-carrying bosons, whereas the photon and the gluon are massless. And because they're massive, it's also a short-range force. that you don't see on the in our everyday life. It's purely at atomic scales. Now, the problem is that if I just write down, say, a Lagrangian, and I put in a term for the masses by hand, I'm going to break gauge invariance, which means all these wonderful things that come from gauge invariance disappear immediately. And so what we would like is a dynamic origin for the masses of these weak gauge bosons. And we get this through a phenomenon called spontaneous symmetry breaking. And for those of you who are working in condensed matter physics, this is an idea that came directly from condensed matter physics and was imported into particle physics and is now right at the very heart of our standard model. So the idea in very brief is, let's start off with a large electroweak symmetry, so a symmetry that connects the weak and the electromagnetic force. And then we have a field, which is called the Higgs field, and this has a non-zero ground state. In quantum field theory, this is called a non-zero vacuum expectation value, which is going to break the symmetry of the vacuum, and this is a procedure called electroweak symmetry breaking. This is the famous Mexican hat potential that we theorize that the Higgs field has. And you can understand this fairly easily, just intuitively, just classically. You can see that this potential has a rotational symmetry. If I rotate it like this, nothing changes. But of course, the ground state is not the most symmetric point. The most symmetric point is right at the top of the hat. The ground state is clearly in this trough. And it doesn't matter. So at some point, my system is going to go to the ground state where the energy is minimized. And then it doesn't matter where I go. I can go here or here or here or here. Anywhere in this trough is going to break that rotational symmetry. So the potential as a whole still has a symmetry. It's only the ground state that breaks the symmetry. And in the language of quantum field theory, this is enough to give masses to the electric gauge bosons, the W and the Z bosons, as well as the charged fermions, but not the photon. And that's important because experimentally we see that the photon is massless. While maintaining the gauge invariance in the Lagrangian, so all the good stuff that I showed on the previous slide, we still have. And then we understand there are quantum excitations of these fields, and this we understand as the Higgs boson. And so if we combine QCD, the theory of the strong interactions, the electroweak theory, and Higgs mechanism, we get something called the standard model of particle physics. Importantly, because of this Higgs mechanism of electroweak symmetry breaking, it's mathematically consistent, and it's also fairly concise. And by concise, I mean you can go to a certain gift shop, and for 20 francs or something like that, you can buy a coffee mug that has the Lagrangian written on the side of it. So just to quickly, you see, I've only been able to talk about electric symmetry breaking, so I don't think you can study.
Fantastic.
So just to quickly just explain the particle content of the standard model. In this picture, on the outside, we have the spin half fermions in a sort of a reddish color of the quarks. These are the particles that feel the strong force. They're things that the blue ones are going to talk to. They also experience the electromagnetic force, so they have an electric charge, and they also experience a weak force, and they have a label, a quantum label called labor. Again, this is more or less an arbitrary label of up, charm, top, down, strange, bottom. Then at the bottom, we have the charged leptons. These feel the electron and its heavier cousins, the muon and the tau. These experiencing weak and electromagnetic force. And here we have the neutrinos, which experience only the weak force and therefore don't really play much of a role in most LHC experiments. One circle further in, we have the gauge bosons, the photon, and the gluon for the QED and QCD, so electromagnetic and strong. Those are the massless ones, and then below it, the massive W and Z bosons for the weak force, that mediate the weak force. And right in the center, we have the Higgs boson, which is a spin zero scalar.
So there's some Higgs potential where you don't have this spontaneous symmetry.
Yes.
Is it possible to like investigate that?
Yes. Okay. We'll get there in a moment. Okay. We'll get there in a moment. Because I touched on this very briefly in my next slide, but we can. I don't actually have a backup slide for this, but we can also talk. I can sort of go off track and talk a bit more about it. Okay. So remind me if I don't in the next slide. So just to give you an idea of the masses involved, but the mass of the proton is roughly 1 GeV, the mass of the electron about 3 orders of magnitude smaller, and then the masses of the typical masses of the particles here, the top mass, which is the heaviest fundamental particle we know, is 173 times heavier than a proton. The Higgs is 125 GeV, and the W and Z around about 80 and 91 GeV. So typically, when we're talking about the energy scale for these sort of processes, where we're interested in producing these sort of particles, we're looking at energy scales of roughly 100 to maybe 1,000 GeV. That's going to be important in the next few slides. So all of this was theorized in the 50s, 60s, and 70s, but we had to wait until 2012 when I was writing up my PhD to actually discover the Higgs boson and have not only a mathematically consistent and concise description of nature, but also a fully experimentally verified one. But of course, all good science, once you make a discovery, it just raises new questions. And perhaps the simplest question is the standard model that is the Higgs boson that we found at the LHC really exactly the Higgs boson that we have theorized in the standard model? And there are a couple of weird things about it. For a start, this potential is incredibly simple. This is basically the example you give when in like lecture 2 of an introductory course in quantum field theory. So it's weird for a potential like this to be sitting at the heart of everything that we know. So is this really what is realized in nature? Now, to your question, we know we have to have a potential that does break electric symmetry because we see electric symmetry break. Okay, it's not strictly speaking true. If you would like a potential that doesn't break the electric symmetry, you have to come up with your own theory that explains the standard model, which is very different. So we can assume we have a potential that does break the electric symmetry. But I can add another term with it, right? I can add a 5 to the 5, 5 to the 6. 5 to the 5 is difficult. I can add a 5 to the 6 potential, which makes this, and I can make sure that all the coefficients are such that I still break the electric symmetry. And then I might still have, but then I don't have exactly the standard model Higgs. I'll get back to that in a moment. So then you can say, look, I know that there is Higgs, induced electric symmetry breaking is responsible for the mass of elementary particles, but is it the only thing that's responsible? Maybe there's some other mechanism that's hiding. The Higgs is a scalar field. Scalar fields are weird. We don't see any other fundamental scalars. So is Higgs really a scalar? And in order to understand this, we really need an in-depth investigation of the Higgs boson. So we're like a kid that has a new toy. If you give a kid a new toy, they don't just put it away and go away. They play with it. They poke it. They try and understand it as best they can. Okay. 2 quick things that I can say to motivate understanding this and to show you how important these questions are. So I told you that the Higgs mechanism gives mass to the fermions. It does so in such a way that down quarks happen to be slightly heavier than up quarks, roughly twice the mass. Now, you know that in a neutron, there are 2 down quarks and 1 up quark, whereas in a proton, you have 1 down quark and 2 up quarks. Because of that, the neutron is very slightly heavier than the proton. That means that neutrons decay to protons, but protons don't decay to neutrons. If it were the other way around, protons would decay to neutrons. You would never be able to have a stable proton to form the nucleus of a hydrogen, which means you would have no stable hydrogen, which means you don't have no stable elements. You'd have no stable stars. You'd have none. You wouldn't have any of the complex structures that we see. So this is what the Higgs mechanism does. Yeah.
So this mass hierarchy of the positively charged part and the negatively charged part, that's actually opposite for the other generations.
Yes. So in the other generations, exactly. So the bottom
explanation.
no. So very good. So this is another question. So essentially, what the Higgs mechanism does is it changes the question. So the reason why the masses of the quarks are like they are is because of how they couple. It's called the Yukawa coupling to the Higgs field. Which means that you should see when you measure them, you should see that if you measure their couplings to the Higgs, they should be proportional to the mass. So what we basically have done is we've sort of shifted the problem. We've kicked the can down the road. So the answer is why is the down heavier than the up? Because the down Yukawa is bigger than the up Yukawa. Okay, why is that? That is still unknown. There are theories of new physics that attempt to explain it, but they are just theories. There's no experimental evidence. It's a big, important, unanswered question. Okay, I can say something else very briefly, but I didn't. I actually took out the slide for this because I thought it wouldn't be that interesting. But I can just try to draw it very quickly. Find some chalk, which is related to your question. So if I just draw this this Mexican hat potential in profile, I get something like this, and this is my vacuum state. Right? You have to imagine that I'm rotating this in 3 dimensions. But imagine I don't have something like this. Imagine I have something like this, right? Now this is a minimum of the potential, but it's a local, not a global minimum. Now, if we are in this position, then you might say, okay, that's fine because I have a potential barrier that I can't get over in order to get there. However, this is quantum mechanics, so you know that quantum mechanical things can tunnel. So we can have some quantum tunneling from this position down to this position. This would entirely change the vacuum expectation value, which would entirely change all the fundamental properties of all the particles that we have. It would change the masses of absolutely everything. So if this were to happen in an instant, in the speed of light, everything that we know about the universe would completely change. Physics, chemistry, the lot. It would be the ultimate catastrophe. We would completely cease to exist.
Yeah, so in additional minimum that requires the 5 to the 6.
Yeah, exactly. You need an additional term. Exactly.
The 5 to the 6 is irrelevant thing, so it's going to have a small coefficient compared to the other.
Exactly.
So can the shape like this still occur?
Yeah. You can cook up a model that will do this for you. Absolutely, yes. Now, depending on your model, the lifetime of this tunneling can change dramatically, and I can tell you that the tunneling, the lifetime must be at least of the order of billions of years because we're here, right? But it doesn't mean that it, doesn't really tell you anything more. And the only way we can understand this is to understand the Higgs potential, which is why people do things like looking for dynamics. Okay. So I hope I've convinced you that there's a very rich Higgs phenomenology. You can study its fundamental properties, like its mass, its spin. You could look at how it couples to the other standard model particles. This coupling should be proportional to the mass. That would verify that it really is the Higgs mechanism that's giving the masses to the particles. The Higgs couples to itself, and that tells you a bit about the potential. You can look at its behavior at high energies. It's something that I'm particularly interested in. And over the lifetime of the LHC, which is the next 15 to 20 years, the experimental precision on most of the Higgs couplings to other particles, which is shown over here. And I don't know if you can see the x-axis. So this is 2%, and this is 4%, this is 6%. So you see that over the lifetime, the experimental reach will reach the level of a few percent. And so if we want these to make use of these experimental measurements, we need theory predictions at the same level of precision. Okay, now I've been singing the praises of the standard model for the last 10 minutes or so, so let me say some of its shortcomings. So it's clearly not the full theory of nature. It doesn't include gravity, as I mentioned. This is an incredibly difficult. But beyond that, there is an enormous amount of evidence from our astrophysics and cosmological colleagues to say that there should be dark matter. Standard model does not have a dark matter kind. We also have evidence that neutrinos should have masses, which allows them to oscillate. There's no mass term for the neutrinos in the standard model. The standard model can't explain the asymmetry between matter and antimatter. There's also more, let's say, theoretical problems like the hierarchy problem, or sometimes called naturalness. And all of these require some beyond the standard model physics. So we typically say BSM physics. Okay, and we've looked very, very hard at the LHC, but as yet we haven't found any direct, incontrovertible evidence for new physics at the LHC. What we have been able to do is set a bunch of bounds on, say, the masses that any new particles would need to have. They all would need to be in the range of about a few TeV, so already 5 to 10 times heavier than the heaviest known particle, the top quark, and we've ruled out large areas of the parameter space, for instance, for how they would coupled to the standard model particles. So since we haven't found any direct evidence, something sticking out like a sore thumb, we can say, well, look, we see lots of standard model production processes. We can in each of them, we can measure lots and lots of different properties. So maybe we can see the traces of beyond the standard model physics in a standard model production process. This is what I did with some of my colleagues a few years ago. We looked at the standard model process of producing a Higgs boson together with a Z boson. And then we played around in black is what happens in the standard model. And then we fiddled around with the coupling of the Z boson to the Higgs boson, changed this parameter a little bit, and we got these three different lines. And so you can imagine measuring this quantity, and if you see something that differs from the standard model, even though you only measure the standard model process, you say, aha, there's something fishy going on here. So you need to understand, well, how well do I need to know the standard model in order to do this? If I'm going to look for new physics and standard deviation. So let's imagine that I have some new physics at an energy scale that I call lambda new physics. And this energy scale should be higher than the reach of the LHC. So let's say one to a few TE, so about 100 times 10 times the mass of the Higgs. This is generally speaking too heavy for direct production of the LHC. But you can imagine writing this new physics by adding new operators to your standard model Lagrange. These operators, the standard model Lagrange has a mass dimension of 4. So you can imagine adding dimension 6 operators, and these should then be suppressed by some scale, the scale of the new physics. This is very much analogous to the Fermi theory of weak interactions. Then the effect on the standard model observables should be given by Q squared over lambda new physics squared, where Q is the typical energy scale of the standard model interaction, which, as I've said, should be around about 100 GeV, which is roughly the mass of the Z, the W, the Higgs, etc. And so if you take 100 GeV squared divided by a few TeV squared, you get something at the level of a few percent. So that's the discrepancy we would expect to see between the standard model prediction and some new physics that's hiding that makes itself known through a standard model interaction. And so this tells you we need to have control of the standard model processes once again at the percent level. So I hope I've motivated this high precision program in particle physics, both on the experimental side as well as on the theoretical side, partly to fully explore electric symmetry breaking through the Higgs mechanism, and also to make sure that we're not missing any new physics that might be hiding from us. Since we spent billions of euros on this machine, we may as well make full use of it. Yeah.
So, was there some motivation that we have to look at this boson? What was the motivation for that specific projection?
Okay, it's okay. This becomes a little bit complicated. So if you want to write down a full set of these dimension 6 operators, by the way, you start at dimension 6 because dimension 5 you can show that the number of operators is very restricted. It's basically just neutrino mass, so it doesn't really have any effect on the Large Hadron Collider. So you start 109. Now, if I remember correctly, if you take into account Lorentz invariance and a few other symmetries, you get 2,499 such operators. You can then impose some additional flavor symmetries, and you can reduce it to a few hundred. But clearly, so then you have two approaches. One approach is you take a whole bunch of standard model processes, a whole bunch of observables, and the predictions from a whole bunch of these things, and you throw it all together and you do a gigantic fit. Okay, and that's one option, and people do that, and it's very important. What we did instead is we said, okay, let's look at one specific process. Let's look at some specific operators that would exist here, and let's see. So you have a problem. The problem is you don't want to see a discrepancy and then say, oh, I found some new physics, but it's actually just a higher order correction to your standard model process. What I mean by that, I'll get to it in a moment. So you want to know that if you see now I can use different color. So if I have a standard model prediction that's something like this, and what I see is something like that, I might say, oh, great, I've seen new physics, I booked my air ticket to Stockholm to get a Nobel Prize. But then somebody like me comes along and says, look, I do a perturbative correction, the standard model prediction, and I get exactly that. And then you have to cancel your ticket. So that's what we were interested in looking at. To what extent can we understand the interplay between new physics and higher order corrections to the standard model? That was the motivation for that particular work. Now, I've said all this before. I've told you about higher order corrections, so I'm getting the order a bit wrong, but we'll get to that in a moment. Yeah.
I guess you could naively do the same thing with Fermi theory, and you don't know that
Absolutely.
absolutely somebody does an exercise and see.
Yeah, you can absolutely do that. And so what you do is you imagine you take, say, beta decay, and you run, so Fermi theory, if you run into very high energies, you'll see that the decay rates that it produces will diverge. So they will go to infinity. And the reason is that it's only valid below some scale, which is given by the masses of the W and the Z boson. So you can absolutely do this. And then you will see at some point, you can plot as a function of energy your decay rates versus what Fermi theory gives. And at some point, Fermi theory will go off to infinity, and the electroweak theory will give you exactly what you need. And this exercise was done probably for the first time in the 80s when the standard model was first rarely tested. When say the W and Z bosons were discovered. I must admit I haven't done this full exercise myself, but I at least can see that working with the Fermi theory, I can see the energy dependence, and I can see that it's going to go to infinity, which it clearly cannot. Okay. So now you can ask, I hope you can see this. So I want to be able to do make theory predictions at the percent level. And so you can ask, well, is this even possible? And at first thought you might say, well, I have a bit of a problem because I told you that the LHC collides protons, so we should be looking at the strong interaction, quantum chromodynamics. The problem is the QC Lagrangian is written in terms not of protons, but of quarks and gluons, collectively known as partons. And the protons, on the other hand, those are the fundamental objects, quarks and gluons. Protons are composite objects made of quarks and gluons that are strongly coupled and confined within a proton or a neutron. The QC Lagrangian is not solvable, and so it's very difficult to understand proton dynamics from first principles. So we already have a problem where what our experimental setup doesn't match up. And we're saved by a phenomenon called factorization, which basically says that if you have phenomena that occur at different energy scales, you can treat them separately. So I can imagine that this is my condition. I have a proton coming in over here. I have a proton coming in over here. This is made up of a whole bunch of quarks and gluons. I select one of these quarks and gluons from each of the protons, and it has a hard interaction. By hard, I mean the energy scale is about 100 GeV to 1 TeV. This is where the standard model-like stuff happens. This is where you produce Higgs and tops and all that fun stuff. On the other hand, the protons in the beam or the hadrons that you find in the detector, their energy scales is the proton mass or the hadron mass. So around about 1 GeV, 2 orders of magnitude smaller. So you can really factorize the theoretical description of what's happening in red and what's happening in blue. And you can make this more than just a picture. You can turn this into a theorem called the factorization theorem. So on the left-hand side, we have a physical observer. That's something that someone like Deepak goes and measures at the LHC. Inside this integral, I have this quantity. It's called a platonic cross-section. This is what describes this hard process that occurs at the energy scale of electroweak physics, 100 GeV to 1 TeV. So this involves the fundamental particles of the standard model, quarks and gluons, as well as W bosons and top quarks and Higgses and all that fun stuff. And so this has the phenomena that we are most interested in investigating as a broad statement over the LHC. And there's a wonderful property of the strong interaction called asymptotic freedom, which tells you that the strong coupling, which is this alpha S, at these energy scales is small. It's roughly about 0.1. It's a small parameter. And as physicists, as soon as we see a small parameter, we say, okay, fantastic, I can use perturbation theory. Because realistically, that's all we know how to do. Okay, so I have to integrate this, technically speaking, it's a convolution. So I have to convolute these with something called parton distribution functions. Those are these objects, and this basically tells me how my partons, my quarks and gluons, are going to behave inside the protons. And so this is going to be energy scales of roughly the proton mass, 1 GeV. Now, these are not directly calculable from first principles. We extract them from the data by taking some well-understood processes like Raoul production or deep inelastic scattering. That's where the name of the workshop comes from, and comparing theory with data. And so, of course, it's an interplay here, because if I have a better theory prediction, I can get a more precise extraction of my PDFs. The current precision on these is, let's say, between 1% and 5%, depending on the exact scenario. And there are a lot of efforts to try and improve this determination, the precision of the determinations of PDFs, including a very large and active group at my university in Milan. So after this hard interaction over here, we send out a whole bunch of partons, quarks, and gluons, and they radiate off a bunch of stuff. Now, when we try to theoretically describe this sort of radiation, we have a bit of a problem, because we get these large logarithms in certain regions of the phase space that can ruin our perturbative convergence. I'm not going to say too much about this, other than to say that there are two ways of treating this. One is an analytic procedure called resummation, and the other one is a numerical, a Monte Carlo procedure called parton shuttles. The analytical solution, as you may expect, gives us a lot more control. It's more precise. Whereas numerical approaches is less precise, it has less control. But the analytical solution is much more limited, it's less general. So typically, when we do an analytic approach, we have to look at one particular observable in one particular production process, whereas the numerical approach is frequently applicable for a whole class of observables in a whole class of processes, often being in all processes possible. So there's a trade-off with which one you want to use. Oh, and then finally, this is not an exact formula. There are corrections to this formula, which encode non-perturbative effects, such as, for example, hadronization. And these effects, we don't control. These are very poorly understood, but they're typically at the few percent level. You can understand that they're at the few percent level because they're power suppressed by the QCD confinement scale, lambda QCD, which is order a few hundred MeV divided by Q. And Q should here be the scale, the lowest scale in the hard interaction, so typically around about 10 GeV. And N is just some integer number. So even for N is equal to 1, you get a few percent. If N is equal to 2, then the suppression is even greater. So we're very happy because in principle, we can now compute things using perturbative QCD and using this factorization theorem with a few percent accuracy, which is what we said was the aim. But doing so isn't easy. It requires advances in basically all these aspects, in the extraction of PDFs, perturbative techniques to treat, fixed order techniques to treat the hard scattering, better tools for resummation, better algorithms for parton showering, better modeling for hadronization, and so on and so forth. And you can, and people do, spend an entire career working on one or maybe two of these areas. And I don't think there's a person in the world who's an expert on more than 3 of them. And certainly includes these. I'm going to tell you the stuff that I'm working on, which is the topic of fixed order calculations. Okay, so in order to understand this, we can do a perturbative expansion in the strong and electroweak coupling. So the strong coupling, I said, is around about 0.1. The electroweak coupling is about an order of magnitude smaller. So if I have some interaction that I get a photonic cross section, I can write down a leading order, and then I can add one QCD interaction. I pay a price with a factor of alpha s, which means this correction is going to be roughly 10% of this limit. I then do a second QCD interaction, and I get a correction at the level of alpha s squared, so about 1%. And then I can add further and further corrections. I could also add electroweak corrections, and in the first one, I'm going to be suppressed by about 1% because the electroweak coupling is 0.01. And then I can mix the two up, so I can have something like alpha s. Now, these numbers are very rough order of magnitude. In certain cases, it's much, much larger. In some cases, it might even be smaller. And of course, like any perturbative series, the more terms I compute, the more precise I get. But each term is an order of magnitude or more complicated to compute than the second one. So this is fairly easy. This is difficult-ish. This is very difficult. This is very, very, very difficult. Yeah.
Well, so no, actually, it's on the factorization.
Yeah.
So maybe I always say, okay, it does not know.
Okay, if one of these guys were here, they would attack me. So in Q, my understanding is it's only proven the proton-proton collisions for Rayleigh.
Okay, so that's not, okay, that's not. To what extent is this all based on this expansion?
Yeah, so even so even when you go to third order, it's not clear. So it's known that collinear factorization, which and I'll get to that in a moment, breaks down at third order increasingly. And for a long time, people worried that this meant that the factorization theorem broke down. However, there is some work that basically actually we had a talk at Aspen from Neumann, from Matthias Neumann. There is some work that suggests that the thing that breaks it is something called Glauber gluons. And you have to include Glauber gluons in another part of the calculation, and basically the two effects cancel out. So you still get the factorization here. But this is definitely, with a lot of caveats on this. It's only for very simple processes. This is still very much something that we're trying to understand.
It's really conjecture.
It's a conjecture. It's a conjecture. Now, what I can say is that also so people do compute up to this order. I'm not going to discuss it today, but people do compute up to this order, which, as I've written here, is needed for some processes. In most cases, if you want % level precision, you're happiest going to N and a low QCD, and next leading order electroweak, the stuff in red, that's the 1% level. Anything below that is typically below the % level, and so you need it for certain, typically very simple processes. However, there's a bit of a problem in doing that because you determine these PDFs to a given perturbative order, and they're not known beyond next to leading order. There are approximations or incomplete results for n cubed alone. But when so what people do is they compute this object to n cubed alone, and then they convolute it with next to leading order PDFs. Now, formally, the result that you get is infinite if you do that, because you don't cancel all the collinear poles, but people still do it. Okay? Yeah, exactly. You're physicists, not mathematicians, and you basically say, look, because if I spend forever, and my name is Bernard Misselberger, and I spend forever computing this correction, and some PDF people haven't got an n cubed PDF, I don't care. I'm just going to convolute it with whatever is on the market, and know that at some point the PDF people will catch up. It's much like there's an interplay between all these different communities. And it's a bit like the interplay between theory and experiment. So if I know that there's some experimental quantity that over the entire lifetime of the LHC is only going to be computable with a 10% precision, I'm not going to do an NNLO calculation for 1%. It's a waste of my time. I have better things to do with my life. But on the other hand, if some experimentalists come in and say, oh, look, we've had a brilliant idea, and this 10% that we thought we could get, we can now get it to 2%. Okay, these guys are, they know what they're doing. I better, start doing this calculation. And it's kind of the same thing here. If the fixed order community starts pushing the envelope and getting n cubed results, that forces the PDF community to start developing. If the resummation people, or let me say the other way, yeah. So if the resummation people start looking at the Parton-Shao algorithm and say, you guys aren't as accurate as you think you are, then the Parton-Shao algorithms get better. So there's always an interplay between these two things, and so which is good because we kick each other's asses to make us all work harder and come up with better ideas. Okay, so let me talk a bit about how these predictions are. So I realize I'm dramatically over time. I still have 10 minutes. Okay, well, I'm only about a third of the way. Okay, so then I'll just try and get to the problem of infrared singularities, and then maybe I'll stop there, or at least give a very good view of this. Okay, so if we have, so how do we compute these Partonic cross sections? Well, we have to compute something called matrix element, and you can think of this as like the amplitude from quantum mechanics, an amplitude go from some initial state to some final state, and so you can think about the modulus squared in terms of some probabilities. You then need to integrate it over the phase space of all of the final state particles. That basically says I take into account all possible probabilities for all these momentum configurations, and I can relate that essentially to the number of events that are seen in a detector. Now, when we look at these higher order corrections, we have to add additional QCD interactions, and these come in two different types. The first is a virtual, what we call a virtual correction. So here we have a gluon, this stuff in black is my leading order process, and I want to add a QCD correction to it. So I add this gluon, and this gluon goes between these two same fork lines, but its momentum is unconstrained. So we need to integrate with all possible values of this form momentum. It's a virtual gluon. It's not observable. Its mass, its form momentum squared is not necessarily equal to its invariant mass squared, meaning not zero. Or we can have a real emission. So here we radiate a real, honest to God, on-shell gluon whose momentum squared is equal to its mass, equal to zero. And this is observable. This could really become a jet or a hadron, and you can see it in the middle. And these two diagrams really encapsulate the two challenges in computing these higher order corrections. The one is just doing these multi-loop integrals. They're integrals. Integrals are difficult to do, and these are integrals in 4 dimensions if you do it at one loop, and if you add more corrections at next leading order, you have 2. So then you have an integral essentially in 8 dimensions, which is very difficult to do. And just to make matters worse, there are singularities all over these integrals. So you can't just shove it into, a Monte Carlo code and push the button, push enter. You will just get a very, very big number from your Monte Carlo. That's just telling you that there's an infinity there. So these are very different. The second problem is the one I'm going to talk about because in 10 minutes, because it's what I'm spend most of my time on. It's a problem of inferred singularity. So in order to understand this, let's look carefully at this real emission gluon, and in particular, let's look at this propagator over here. Now, I know that some of you haven't yet taken courses in quantum field theory, so you're just going to have to take my word for it. The propagator is the inverse dot product of the gluon form momentum dotted with the form momentum of this particle. You can then write this in terms of the energies and the relative angle between the two of them. And you can, if you take my word for that formula, you can clearly see that this will become singular if the energy of the gluon goes to be 0. That we call the soft limit. Or if the angle between the gluon and this parton becomes 0. In other words, we call this the collinear limit. Now that's a problem because I told you we need to integrate this matrix element squared over the full phase space. That includes regions of phase space that are soft or collinear. And as soon as I hit one of those regions, this integral, because of the singularities in this matrix element, will start to diverge. Divergences are a problem. Divergences are infinities. Infinities tell us that there's something wrong with what we're doing. Now, it turns out that if we look at the virtual amplitude, the one loop stuff that I showed you, this also has divergences. For various technical reasons, we perform these integrals not in 4 dimensions, but in 4 minus 2 epsilon dimensions. And then these divergences show up as poles in 1 over epsilon. So when you take the limit, the epsilon goes to 0, so we return to 4-dimensional space-time, then we get, then these become singularities. And it turns out that we don't need to worry about these divergences because they cancel when we combine the real and the virtual. And this is sort of required because this division into real and virtual is entirely artificial. It's something that we do because it helps organize the calculation in our minds. It's not what nature needs to do. Nature is much smarter than we are, so nature just does it all at once, no problem, and there are no divergences. We have to split it up into 2 pieces, or we choose to split it up into 2 pieces, seeing divergences in each of them, and then combining them and canceling and leaving a physical, in other words, finite result. The problem is that cancellation only happens after you integrate over the phase space. And as soon as I integrate over the phase space, I lose information about this gluon. So if I do this integration and my experimentalist friends come to me and say, well, can you tell us, the behavior of this gluon, what's its transit momentum going to be? I'm going to say I have no idea because I integrated both. There's nothing wrong with that, but of course you want to make as much use of the information that you have from the experiment. So you'd ideally like to extract the singularities without integrating over the phase space of the radiated partons. And you'd then like to make your singularities appear like poles in 1 over epsilon, and you can then analytically see the cancellation of the poles against the virtual corrections, leaving with something fine. This is called a subtraction scheme. The basic idea is, let's imagine I can identify a function, which I call S. And this S should have two properties. First and most important, it should reproduce the matrix element in all the infrared limits, so soft and collinear. And second, it should be relatively simple, and so that I can integrate it over the unresolved fixed space. So then I have my my divergent integral. It's divergent because of singularities in my matrix element, and I simply subtract S and I add it back. Here I'm integrating in D dimensions. Now, when I subtract S, I have an integral that is manifestly finite. Every time I hit a singularity in my matrix element, it is removed by S, by construction. So this is finite, and that means I don't need to worry about doing a D-dimensional integral. I can do this in 4 dimensions, typically in a Monte Carlo numerical. But I then need to add this back, and when I add it back and integrate it over D dimensions and do this integral analytically, I will see these singularities appear explicitly as poles. I can then cancel these against the virtual poles and get a finite result. Now we are hugely helped by an important property of QC, which is that amplitudes in the soft and collinear limits factorize. What do I mean by this? I mean that if I take this process this real emission process, and now I'm labeling the gluon with this weird M, and I take the energy to 0, in other words, I have a soft limit. This is just given by this enormous factor called the iconal function, multiplied by the same process without a gluon. This iconal function includes a product of all, sum over all the external partons, the quarks and gluons, the dot product of pi dot pj, and then downstairs the gluon momentum. And then it's going to give me this dot product of these TIs, which are essentially just matrices in color space. It tells me how the colors work. So this all in all is called my iconal function. Important to note that the gluon dynamics, the momentum of the gluon only sit in this function. They're completely removed from this function by the factorization. And the same is true in the collinear limit. Here, if the gluon goes collinear to this this parton, then I get a so-called splitting function, which is a function of Z, which is a ratio between the energies of these two particles, again multiplied by the leading order of the process without the gluon. So in other words, again, all my gluon momentum is contained in this splitting function. And here I've written as a sort of it is multiplied. Okay. I have 2 minutes. Okay. And the internet connection is unstable. So let me go through this very, very quickly. If anybody is particularly interested, we can talk about it later, and I can give you the rest of the talk. But subtractions at next leading order are fully solved and have been fully solved for about 30 years. And when I say fully solved, these schemes are known analytic. They're fully analytic, meaning I can compute my counter terms analytically. They're fully local, meaning I can do the subtraction point by point. They can be applied to any process at the Large Hadron Collider or any other collider you choose, so they're fully general. And they're relatively easy to implement. You can read a paper and sit down and write a code for fairly easily. They're quite transparent. And this was an essential precursor in the late 90s and early 2000s to the automation of next leading order calculations, for instance, in MAGRAPH. So MAGRAPH has MAD FKS and MAD dipole. That's Catani-Seymour dipole. When we get to next leading order, things become more difficult. Here we have to consider 2 emissions. So let's look at 2 real emissions, the so-called double real. And we have a huge problem with something called the overlap of limits. And there are numerous approaches that have been proposed over the last decade, or say 2 decades or so, including one that I've been working on, so-called nested soft collinear subtractions. And these have allowed a huge number of N and low accurate results in the last 10 years, but none of them are at the same level as the next leading order subtraction scheme. In other words, none of them are fully local, fully analytic, and generally applicable. And so developing and refining these methods is a very active area. And here's just a selection of papers that have come out in the last 2 to 3 years just to sort of illustrate this point. Now, I'm not going to have enough time to discuss. As you can see, I had a lot more planned, a lot more planned. But what I wanted to say is that about 15 months or so ago, myself and my collaborators, 4 of my collaborators, took our method and were able to generalize it in part. So we looked at processes with an arbitrary number of final state gluons, and we were able to show that the poles cancel, and we were able to compute the finite remainder for the processes. For this process. Now, of course, this only includes gluons at the final state, so we wanted to extend it to processes with quarks in the final state, so somehow you have a less symmetric final state. And this is work that's in process and should appear on the archive in the next week or so. Our future work is to generalize this to some multi-quark final state and to finally have the solution that we want, fully general approach, and the fractions at the same level as next to leading order. So I think you've heard enough from me now. Thank you very much for your attention. My apologies for running so horribly over time.
No. Thanks for a great talk. Any questions? Yeah.
So your method can be used to subtract the known effects from beyond the standard model effects.
No. So this is all okay. So there are a couple of questions within that. So in principle, everything I'm talking about is standard model. Okay. So I'm really working within a theory of QCD and only worrying about the infinities that arise from QCD. Now, you can also, with some restrictions, use this for some new physics, but I'm not subtracting, known effects from new effects or anything like that. This is an important problem, but it's a separate problem. All I'm doing is I'm saying I have a calculation that I need to do. I can split my calculation into 2 or 3 components. When I do it, I see that each of these components has a singularity or has a number of singularities. And in order to understand, to treat these singularities, what I have to do is employ the subtraction procedure. Once I employ the subtraction procedure, I basically get a bunch of poles in each of the 3 terms. So I get 1 over epsilon to the 4, 2 over epsilon to the 4, minus 3 over epsilon to the 4, and then I can cancel them. It's a lot more complicated than that, but ultimately I get all these poles in 1 over epsilon to cancel, and then I can take an epsilon to 0 limit, and I'm left with a finite result, which I can then use to make a physical prediction for a cross section, which I can compare with experiment. So that's the, let's say, the brief 1-minute summary.
Yeah, question. So you said like you can do fixed order calculations even at impute data for some things, n squared or for most of the things, right? And you said like PDFs are a limiting factor because PDFs, they're not catching up with. It also isn't partial shower problem because ultimately for us, we have to run things with partial shower, and even another partial shower is
Yes. So there are, let's say, problems with the, partial showers are incredibly important because they're the things that make a connection between the stuff that we do and the stuff that you guys measure. No doubt about that. And there are problems with part-on showers. So very briefly, what part-on showers do is the same as what resummation does, is it resums large logarithms. So you get towers of logarithms of this thing that these methods are supposed to compute. Now, if I do an analytic calculation, I can say that I sum all the leading logs or next to leading logs or next to leading logs. And I know the accuracy. I know a priori the accuracy. This is what I meant by more control. But the problem is I have to work process by process, so it's incredibly inefficient. Monte Carlos are just a numerical tool, so you don't know what accuracy you have. And there were a lot of claims about the accuracy about 6 or 7 years ago. And then the Pan-Scales collaboration really started dissecting these Monte Carlo parton shower algorithms, and in many cases found that the accuracy was not very high. So now, meaning that some of them were not even leading log accurate, so they were not even resumming all the leading logs. And there were other problems. So for instance, if you do Pythia with one of the showers, it's a complete mess. You just cannot do it. And so they made a lot of progress taking parton showers to leading log and next to leading log. And I believe they now have, for some very specific observables, probably an E plus E minus there next to leading log. But the problem then becomes that you need an interface between the fixed order calculations and the parton shower. And this is a whole other kettle of fish, because this is difficult to do at next to leading order, and it is incredibly difficult to do it next to leading order. So yeah, when I said that there are problems all the way down the line. And of course, this, why is it a problem that there's no next to leading, so if I go back maybe 15 years, next to leading order calculations were the state of the art. And there was a method two methods, in fact, to interface these with parton showers, so Powhig and MC at Everett. And then so then at that point, there wasn't a problem of interfacing N and LO calculations with parton showers, until people started doing N and LO calculations. And this is what I mean by there being an interplay. As soon as people say, oh, I don't need to worry about the matching of N and LO with parton showers, while there are no N and LO calculations. Then a bunch of people start doing that, those N and LO calculations, and another bunch say, oh, we better catch up. Now, this is a very, very difficult problem. So this is lagging a lot, in much the same way that the PDFs are lagging. Now, the PDFs are lagging for entirely different reasons. Part of the problem that they have is that they don't have the fixed order calculations that they need to extract full N cubed LO PDFs. So one of the things that they would need would be something like die-jet production at N cubed LO. Yeah, good luck with that. So by next leading order was done recently, and to produce results, it was 100 million CPU. Cubed LO will be at least an order of magnitude. So it is not, some of the integrals, the loop integrals, some of the loop integrals have been computed. It's not known at all how to do this from. Best hope, your best hope would be to take the 3-jet production and slice it. Good luck, because what you need to do is you need to take 3-jet production, which takes 100 billion CPU hours to do when those 3 jets are well resolved, and then you need to push them very close to the infrared limit, which will increase your computational budget by at least an order of magnitude. And by the way, this calculation was only done because you crazy people at Atlas wanted it to be done. It was the theorists who did the calculation did not want to run it. They couldn't run it on their system. It had to be run on Atlas. We theorists do not have the computational resources.
What order of CPUs does OpenAI these days have?
I don't know. No, I mean, okay, of course, if you compare us with other branches of science like protein folding, where this is a drop in the bucket. But I mean, I think the LHC budget, somebody was talking about it at Aspen, I think it's something like order several billion CPU hours. And so we're talking about a single calculation that's using up, maybe not maybe 2 to 5% of the budget. And of course, this is a huge problem because this costs a lot of money. This costs reducing the computational load is actually a very important priority for CERN because it costs them a fortune, for example, in electricity, right? Just to cool all these poor computers that are working so hard.
Could you comment on the largest QCD side? I mean, are there people doing similar computations there?
Yeah, I mean, I'm wholly unqualified to make any intelligent statement about lattice QCD, other than the fact that and you certainly know a lot more than I do. There are people who are trying to push the envelope of lattice QCD calculations for PDFs. This would be wonderful because it will be a first principle calculation. So, for instance, our friend Mattia was looking at this for a while. My understanding is it's still not quite advanced enough to actually be put into practice. Sorry, lattice, not yeah. So it's already you're really taking QCD, discretizing and solving the equation of motion and getting PDFs on the lattice. My understanding is it's still quite a. The last time I spoke to people working on this was a few years ago, and they were saying, "Look, we're making good progress, but it's probably not quite ready yet." And the fact that I haven't heard anything about it means that probably there's still some things to work out. It's a difficult problem because my understanding is that amongst other things, you can't construct chiral fermions on a lattice, if I'm right. And since this is a standard model, is a chiral theory, that's one of the problems that we have. It will be wonderful. It will be absolutely wonderful if this could happen, not least because there are at least 4 different groups that produce PDFs. And of course, because this is it's an extraction from data, so there are lots of different approaches that you can use, and then they get different results, and then they argue about which result is correct. And these arguments can be either highly entertaining or highly frustrating, depending on your attitude at the time. Yeah. Yep. Yeah. Yeah.
So
why am I doing that?
yes, so there's like some imbalance in dimension now.
Imagine I do this in D dimensions, right? I can happily do this. I can't do it in D dimensions. But if I did do it, I can't do it in D dimensions because D is not an integer. And I don't know how to tell a computer to do it on an integer number of integers. I can write down a Monte Carlo with 4 or 6 or however many variables, but I can't do it with 4 minus 2 epsilon variables. But imagine if I do this. This is a finite quantity. Okay, so I'm going to get a finite number plus order epsilon. Here I'm going to get poles, 1 over epsilon squared, 1 over epsilon, order epsilon. Those poles are going to cancel with the virtual. Once I cancel the poles, I take the limit that epsilon goes to 0. Okay, because I want to ultimately return to my 4-dimensional space-time that I like so much. And so all the corrections here are going to go to 0. So I know, and so then I'm able to say, okay, look, I know that beforehand, so I can do this in 4 dimensions. And then I say, okay, great, that's an integer number. I now can put this on an Monte Carlo.
Yeah, I think that's a good one. So thanks. I guess if you have any further
If you have more
questions.
questions, you're welcome to talk to me. I'm here for the next 3 or so hours, 2.5 to 3 hours, so I'm very happy to.
I was actually wondering how obviously the dimension regularization, whether it's virtual groups, but it also regulates this sex indicators.
Is it obvious?
But that's a totally different thing in my mind.
Yeah, okay, so you can if you like, what you can do is relate it to something like the optical theorem. And basically what you're doing is you just say, if I have some right, do the interference of this with itself. So I'm sparing. Then what I'm essentially doing is I'm just making an optical cut through something like this. But I can see this as a 2-loop integral. And I can also make a similar optical cut like this, and then I get the tree level. So you can and there are actually people who are thinking about this, basically saying, look, exactly what I said. Subtractions are not necessary. Subtractions are something that we have to do. You should just use the optical theory and compute both at once. In other words, your loop integration and your phase-space integration at the same time, because they're really the same thing, and that's what nature is actually doing. Now, these techniques are interesting. I haven't seen them. I wouldn't say that they're being fully explored. fully developed, although there are people working very hard on this. But to me, these techniques are still under development.